This is lecture video 44, and I will explain logarithm defined as an integral in this lecture video. So the natural logarithm function is defined through this definite integral. It is defined by this definite integral from 1 to x 1 over t dt, where x here is a positive quantity. So this means that ln x is not defined for 0 and non-negative numbers. So you can also see this by looking at the graph of y equals ln x. As you can see, including the 0, ln x function is not defined for x is less than or equal to 0 because there is no graph here. So let's concentrate on this definition given by this definite integral now. For example, if you choose your x value between 0 and 1, so now you are looking at this interval, then by using this definition for the natural logarithm function, ln x is defined the integral from 1 to x 1 over t dt. But here x is less than 1, remember? So the upper boundary is less than the lower boundary, which means the result of this integral will be negative. Or in other words, so you can just switch the places of the boundaries because the smaller boundary, which is x, is supposed to be at the bottom. So if you switch the boundaries here like this, you need to put an extra minus sign by the property of the definite integral. So now what do we have? From 1 to x, integral of 1 over t dt, this is your 1 over t function, and you are integrating it here from x to 1, so it will give you the area under your curve. Your curve is 1 over t, here it is, and this integral is in fact the area of this shaded, red shaded part, right? So it is something positive, and since you have an extra sign in front, overall thing for ln x, where x is between 0 and 1, is something negative. You understand that the values of ln x from this line, what do you understand? The values of ln x is negative for x is between 0 and 1. Okay, so let's say if this is the case. So this is your ln x function. You see everything about the ln x function from this graph. So if x is between 0 and 1 over this yellow shaded part, as you can see, the images are all negative. And if x is bigger than 1, then this integral corresponds to the area under this curve over the interval 1 to x. So this time, this integral corresponds to this area, okay? And the values are positive, obviously, as it is this area. And if you look at the images of ln x function where x is bigger than 1, you directly see that the images are positive real values. Okay, what happens if x is 1? X is 1 here, and from the graph you already see that ln 1 is 0. You can also understand this from its formal definition. So you insert x equals 1 to the definite integral. Here x is 1, so from 1 to 1, integral of something is obviously 0. Okay, so what about the number e? When we understand this formal definition, we can also look at the values of ln e. So instead of x here, you will be putting the number e here. And from 1 to e, the integral of 1 over t dt is defined as the number e, the value is 1. So e is somewhere here, okay? And the value of ln function, natural logarithm function, at the number e is defined as 1. So 1 is in fact here, so I think we should put the number e around somewhere here. Okay, ln e is 1. Now, if you are considering now the integral rule for 1 over u du, by using this formal definition of ln x, you understand that it is absolute sine of u plus c. Why we are putting this absolute sign here? Because here we understand that ln x is not defined for 0 and negative numbers, so you cannot put any negative integer and negative real number inside ln function, so you have to put this absolute sign to make sure that everything is positive. So this is a new integration rule for us. Okay. So what we have learned here, ln x, if you take the derivative, it is 1 over x. This is something we knew before. Derivative results in 1 over x, and if you integrate, you see 1 over x is integrated as ln absolute sine of x, okay? So let's concentrate on this table now. These are new integration rules for us, which we can cover by using the integration rule of this form. So what do I mean is, for example, look at this rule. Where does it come from? So we can derive it ourselves, like integral of tangent x dx. So tangent x is sine x over cosine x dx. Now we will use a substitution here. Choose your u function as this part. So cosine x is u, then du is minus sine x dx, right? Derivative of cosine is minus sine. And then you can re-express your integral in terms of u's and du's only if you see sine x dx appeared in du, so this is exactly du multiplied with minus 1. So the integral becomes minus du over u, just like we have covered here, right? Minus 1 of du over u is integrated as ln absolute sine of u. Okay, like that. There is a minus sign in front, and since this is an indefinite integral, I have to include this arbitrary constant c. And now we can take this minus sign here to the power of this part, so that you have ln, do also back substitution, u was cosine x, minus 1 plus c. So what you have done, ln 1 over cosine x, so I took the minus 1 power plus c. What is 1 over cosine x? It is, in fact, secant x. So the result is ln absolute sine of secant x plus an arbitrary constant c. So this is how you obtain this first rule here. It comes from the integration of 1 over u as the ln. Okay, let's look at this second rule. So example, let's choose it as an example. We want to integrate secant x dx, okay? Okay, this rule is kind of strange to evaluate, to verify, because normally, okay, this is what? This is 1 over cosine x. Any substitution won't work here. For example, if you choose cosine x as your u, du is minus sine x dx as we did before, but there is no sine x around. That's why this substitution doesn't work. Instead, we will be doing some more, we will be applying a smarter thing, like we will multiply the function with something and divide by it. So, and I accept that this is kind of strange, but when you saw it once, you won't forget that. But without seeing it for once, it is a bit difficult to guess, but we are multiplying with this expression, dividing by it, so that we are still solving the same question. We didn't change the question because we also divide by it. Now I will do these multiplications. Okay, let's do them. What we have, it is secant square x plus secant x times tangent x divided by secant x tangent x dx. Now, after this step, a substitution will work. So let's choose this part, the denominator part, as our u function. So we are applying a substitution. Okay, u equals secant x plus tangent x, then du is, what is the derivative of secant function? It is secant x times tangent x. What is the derivative of tangent x? It is secant square x. So you put the x at the end. That's, you see, this whole thing is in fact what you have for du. That's why the integral can be rewritten in terms of u's and du's in this form, very simple form. That's why the result is ln absolute sine of u plus c. So what was u? You just do your back substitution now. Secant x plus tangent x. So this is how you obtain the rule for the integration of secant x, like this. That's why in our integration table, we have such a rule and it is verified like this. Okay, let's move on. Look at this example. We will choose some part from this function as u and we will apply substitution. Let's choose this part as u. If you have a rational function, something divided by something, the best choice for you is to choose the denominator, okay? 2 plus secant y is our substitution now. Then what is du? 2 is gone. The integral of secant is, derivative of secant is secant times tangent dy. You see, this whole thing becomes just du now, so that you express the whole integral in terms of u's and du's in this very simple form, which is integrated as ln absolute sine of u plus an arbitrary constant c. So what was u? U was 2 plus secant y. So this is your result. Don't forget to don't forget to turn back to your original variable, which was y, back substitution. Okay, next example, which is about ln's. So we will apply a substitution again. Okay, let's try this part. Let's see if it is working or not. So what is du then? Derivative of ln is 1 over the insider part times the derivative of this insider function. So what is the derivative of it? It is obviously 1 over x. Don't forget to put dx at the end. And then, so you see dx over x times ln x is exactly what? This part is exactly du if you choose this part as u. So the integral is then u times du, very simple form, u times du. This is just a power function, add 1 to the power, divide by the same power plus c. So the result is in this form, and you need to turn back to your original variable, ln x. U was this, okay? So let's move on. I think this will be the last example for this lecture video. We have logarithm, and I want to recall you something, logarithm base a, b. So there is a very certain way to rewrite logarithm in terms of ln function. So it is ln b over ln a. So whenever you have logarithm inside an integral, inside a derivation, you have to transform it to ln function because we know how to deal with ln. With the derivatives, with the integrals, we know how to derivate ln, we know how to integrate ln. That's why from logarithm, we need to pass to the ln function. So these are the boundaries, 2 times. Okay, let's write the logarithm function in terms of ln by using this rule. So it becomes ln x minus 1 over ln 2. So logarithm is written like that. Dx over x minus 1. Right? Okay, let's try to write it better. So 2 times ln x minus 1 over ln 2 times 1 over x minus 1. This was denominator like this. Now we can apply a substitution. Let's choose this part as our substitution, okay? So u is ln x minus 1. Then du is what? 1 over x minus 1 dx. You see, if you choose this part as u, this thing directly becomes our du, right? That's why it is possible to rewrite this integral in terms of u's and du's only in this way. So 2 times ln 2 is just a constant in front, right? 2 times ln 2, I can just take it out. This is just a constant. So we have u times du. Let's also transform the boundaries to the boundaries of u. Remember, these are the boundaries for which variable? These are the boundaries for x, but now as I turned my integration to an integration in terms of u, I need to transform also the boundaries for the boundaries of u. Okay, if x is 2, what is u? Then u is ln 1, so it is 0. If x is 3, then u is ln 2. Okay, so these are the new boundaries for the function u. The lower boundary is 0 and the upper boundary is ln 2. From here, we can quickly complete our computations. So the result is 2 over ln 2. How do you integrate u function? It is u square over 2. Now you need to insert lower and upper boundaries for your u function. This is a simplification. That's why the result is 1 over ln 2. You insert ln 2 squared it, and then you insert 0 squared it. So the result is just ln 2. Okay, I want to emphasize something again. Sorry, this is too dark. ln 2 and 0 are the boundaries for u, where 2 and 3 are the boundaries for x. If you are applying a substitution for a definite integral like this, when you rewrite your integral in terms of u's and du's, you cannot write here just 2 and 3 as before. No. Instead of 2 and 3, you need to write the new boundaries, which are the boundaries for u. And from this line, you can see what is u when x is 2, what is u when x is 3. So this is the result. I stop here. Thank you for your attention.